Hello friends, this video on Haloalkanes and Haloarenes part 25 is brought to you by examfear.com. No more fear from exam. Hello friends, this video on Haloalkanes and Haloarenes part 26 is brought to you by examfear.com. No more fear from exam. Hello friends, this video on Haloalkanes and Haloarenes part 27 is brought to you by examfear.com. No more fear from exam. Hello friends, this video on Haloalkanes and Haloarenes part 28 is brought to you by examfear.com. No more fear from exam. Hello friends, this video on Haloalkanes and Haloarenes part 29 is brought to you by examfear.com. No more fear from exam. Hello friends, this video on Haloalkanes and Haloarenes part 30 is brought to you by examfear.com. No more fear from exam. Correct. So we'll talk a lot about strong nucleophile, weak base, strong base. Let's understand what are nucleophiles and what are these. So if you see, the strong nucleophiles are generally the one which has negative charge, full negative charge. If it has full negative charge and no steric hindrance, it will be a strong nucleophile. For example, all these OH minus, because NaOH, if I say, that is nothing but Na plus OH minus. Correct? This is nothing but OH minus. Similarly, KOH, if I say, it's nothing but OH minus. Correct? So, NaI, I say, it's nothing but I minus. So, these are all my strong nucleophiles. It may be a weak base, it may be a strong base. For example, NaI, if you see, is nothing but Na plus and I minus. Since I minus has a charge, it is a strong nucleophile, but I minus is a weak base. We all know that. So, this is a strong nucleophile and weak base. If we talk about NaOH, it gives Na plus and OH minus. Since OH minus has a charge here, it is a strong nucleophile. Because for nucleophile, one thing that matters is the charge, and we know OH minus is a strong base. So there can be a compound which is a strong nucleophile, strong base, strong nucleophile, weak base. Correct? So we're talking about nucleophile. The strong ones are the one which has charge, the weak ones are the one which are neutral. So when you talk about the nucleophile perspective, it's only the charge that matters. But when you talk about the base perspective, you have other thing that matters, right? We know which is strong base, which is weak base. So if you don't know about these, you can watch my class 11 videos where we talk about acid-base reaction, where we talk about the strength of the base, right? The strength of the base. And as I told, the basicity and the nucleophilicity is almost same phenomenon, except that if you see, when you talk about the base, it is donating lone pair to hydrogen. But when you talk about the nucleophile, it donates lone pair to any other. So when you talk about nucleophile, as I told, it will attack carbon. It will give lone pairs to carbon. But when you talk about the base, it will attack hydrogen. So that is the only difference, right? The base attacks hydrogen and nucleophile attacks any other atoms. In our case, since we are talking about organic chemistry, we generally talk about carbon. So nucleophile attacks carbon, base attacks hydrogen. Right? So when you want a strong nucleophile, it has to be a negative charge. Weak nucleophile, no charge. That's the only difference. Because if you see water, HOH, it has lone pair. It has ability to give lone pair of electrons. It is a nucleophile, but it's a weak nucleophile. Why? It is not charged. Correct? Now when you talk about base and weak base and strong base, again you have to refer to the class 11 videos where you talk about which one is strong base, which one is weak base. So both are different. Nucleophile attacks carbon, base attacks hydrogen. For a nucleophile to be weak or strong, the only thing that matters, the most critical thing is the charge. Obviously the steric hindrance matter because we'll take you through the example where we have something like this, right? O minus, and we'll see that this is a little weak base. Why? Because it is very bulky. It will not be able to attack, it will not be able to reach carbon at all. So it's a little weak base because of the steric hindrance. But generally, if it has negative charge, no steric hindrance, it has to be a strong nucleophile. Correct? So for example, I took where it was this I minus is a strong nucleophile because negative charge, but it is a weak base. OH minus again a strong nucleophile because of the negative charge, it is a strong base also. Correct? For example, I told NaOH is a strong base and good nucleophile. Why? Because OH minus, NaOH is nothing but OH minus. Correct? Because NaOH is a very strong base. It will easily disintegrate into Na plus and OH minus, right? This we have discussed. So now, when this OH minus, now if you see, I'll take one compound here. So let's say I have this compound here. This is my compound. This is a hydrogen here. Now if I put OH minus here, there is NaOH. Now if this can happen, that this OH minus can attack this hydrogen. So if it attacks this hydrogen, this is acting as a base. And if this OH minus attacks this Br minus, or not Br minus, sorry, this carbon, which has this Br minus, this carbon it attacks, right? This is acting as a nucleophile. So it is all same, right? This OH minus, when it is attacking hydrogen, it is acting as a base. When this OH minus is attacking carbon, it is acting as a nucleophile. Please understand, this is a very critical topic or concept here. When this particular compound, you can say OH minus, attacks hydrogen, we call it as base. When this compound attacks a carbon, we call it as a nucleophile. One good example can be, for example, this is I, this is me, and this is, let's suppose, you as a student, and this is, let's suppose, my dad. So if I interact with you, I am a teacher. If I interact with my dad, I am a son. So I am the same person. When I am interacting with you, I am a teacher. When interacting with my dad, I am a son, right? So, or if I'm interacting with my son, I'm a dad. Or I'm interacting with my wife, I'm a husband. So that way, I'm the same person. Depending on whom I'm interacting with, my role has changed. Same OH minus, when this guy is attacking a hydrogen, this is a base. Same OH minus, when this is attacking carbon, is a nucleophile. Hope with this you got a clear picture of what is nucleophile, what is base. Both are same compound, right? But it all depends whom they are interacting with. Are they attacking hydrogen? Are they attacking carbon? So that tells whether it is a base or a nucleophile. Correct? So they are not different compounds, they are same compounds. So factors that affects nucleophilic character. I'm talking about the nucleophilic character where the nucleophile attacks carbon. So that is charge, electronegativity, the solvent which we are using, and the steric hindrance. But when we talk about the factors that affects basic character, there are only two factors, that is charge or electronegativity. So when you talk about a compound is basic or not, we don't care which solvent we are using, we don't care about the steric hindrance. But when you talk about the nucleophilic character, for example, this is my OH base attacks a hydrogen, right? So in this case, when you talk about the base, we talk only about the charge and electronegativity of the compound. But when we talk about the nucleophilic character, we talk about four factors, right? So these two factors are common for nucleophilic character, and that's why you see there are some compounds which are good base, weak nucleophile. I mean, there are some combination. We'll take you some examples. So let's understand the factors that impact my nucleophilicity and basic character. The first factor, as I told you, was charge. The electron density increases, the nucleophilicity also increases. So electron density, how it will increase? If you decrease the mass, the density is what? Mass by, charge by mass, right? Charge by mass. Very clear. Or charge density I'm talking about. Charge by mass. So increase the charge by removing a proton. The mass will also decrease. So you are increasing the charge and decreasing the mass. So overall this whole thing is increasing. Right? You are increasing the numerator and decreasing the denominator. Overall the compound is increasing. And that's why the conjugate base is always a better nucleophile. You see, this is a good base and good nucleophile also. So from H2O, if I remove one hydrogen, I am decreasing the mass and I am making it OH minus, I am increasing the charge. That means the charge density is increasing. So that's why OH minus is always a better nucleophile than H2O. Similarly, from phenol, I remove one hydrogen, I got this, and this is a better nucleophile than phenol. Same thing here, NH2 minus is a better nucleophile than, NH3, and SH minus is better nucleophile than SH. And this carboxylic acid also, if you remove a hydrogen, you get a better nucleophile than carboxylic acid. That was the charge. The next was the electronegativity. So if you increase the electronegativity, the nucleophilicity decrease. So fluorine is more electronegative. And less nucleophilic. Similarly for carbon, it's other way around. Let's talk about the solvent now. This is the critical one because this factor will not impact the basic character, but it will impact the nucleophilic character. Correct. So as I told, the protic solvent, if you have a protic solvent, and the protic solvent is the one which can donate H plus, right? So if the solvent which is protic, we can which can give H plus, what it will do is it will make the nucleophile less reactive. How? For example, I have an I minus, and if it's a protic solvent, for example, water. So water will do what? It will form a shell on this I minus, right? It will trap this I minus, and I minus won't be able to react. This is similar to what we have seen in the soap, right? The mud is trapped in the soap. Similar to this is trapped now, right? This was I minus here, this I minus is totally trapped with protic solvent, because protic solvent have, you see, this is all positive charge, right? That's positive charge, positive H. This will trap the I minus, and with this will become a weak nucleophile. If you see in a protic solvent, my I minus so before this, let's understand this line. So this ability of this nucleophile to participate in the H bond decrease as we go down. So this will fluorine, chlorine, bromine, iodine. I took a wrong example of iodine actually. Fluorine, if you take this fluorine will be trapped more. I'll show you why. So if you go down the group, the tendency to form hydrogen bond decreases. Why? Because the size increase. Now if I see iodine here, similarly iodine, so you'll have less trapped, maybe 1 or 2. It is iodine. But if it is fluorine, this is fluorine. This is more trapped. Chlorine will be little less. So if you see, fluorine is least reactive in a protic solvent. Why? Fluorine stand alone is a good nucleophile. Why? Because if you see the charge to mass density, the mass is less. Charge is all same in all three, right? Fluorine, chlorine, bromine, iodine, but the mass is less. So it is a good nucleophile stand alone. But the moment you put in a protic solvent, this is a protic solvent, what happened is fluorine has a high tendency to form bond with hydrogen, H bond. So this will be trapped. Fluorine will be trapped. So fluorine will become a very weak nucleophile because it is trapped in a protic solvent. But if you see in a aprotic solvent where there is no hydrogen bonds, fluorine is the best guy. He is the best nucleophile out of fluorine, bromine, iodine. So hope you understand the fluorine, who was the best nucleophile in an aprotic solvent, became the worst nucleophile in protic solvent because the fluorine got trapped with hydrogen bond. But iodine, which was the worst nucleophile in a normal solvent, because iodine, the charge is same, the mass is huge. But when you talk about the protic solvent, the iodine is almost free, but the other halogens are not free, right? This guy is almost free. Even if this is weak, since he is free, he is more reactive. Hope you understand what is happening here. Fluorine as standalone is very reactive. It's a very good nucleophile, but when this protic solvent is totally trapped. It's totally trapped by hydrogen bonds. It can't do much. So it is like a very strong tiger, but you have put in the cage. The tiger can't do anything, right? The tiger can, even if you are standing here, and there is a tiger in the cage, the tiger won't eat you, right? The tiger won't eat you. But if the tiger is out, he'll kill you. Correct? So you can say that the fluorine is a tiger, or you can say my iodine is a dog, right? You see, tiger is more dangerous than dog, but in the normal scenario, right? And you are a human, you are a human, as a you are the carbon, you are a carbon. As a normal scenario, the dog will not bite you unless the dog is mad or you hurt him. But the tiger will kill you. Even if you love him, most probably he'll kill you. But now in this case, if the tiger is trapped and the dog is not trapped, I mean, if you are in a zoo, if you're standing, right, there is one tiger, there is a tiger which is in a cage, and there is a dog who is out. There is a dog who is out. So which one is more risky for you, dog or tiger? Obviously dog, because dog is out. He's in the open space. He can bite you. But the dog, even if it is scary, it can't do anything because he's totally in a trap scenario. Same thing here. Fluorine is a very strong nucleophile, but totally trapped by hydrogen bond. It can't do much. It becomes weak in a protic solvent, but in aprotic solvent, it is very strong. So that is the real life example of the nucleophile. Now we'll talk about the steric hindrance. That also plays a critical role in the nucleophilicity. If it is, for example, in this case, this carbon, this is totally bulky, right? This will be less reactive. You see, all these have a negative charge. All these have potential to be all these are nucleophile, but because of more steric hindrance, more bulky, this guy, this is less. Yeah. So if you increase the bulky is the nucleophile, the lower is the nucleophilicity. Let's talk about some of the nucleophiles and base, and let's see if they are strong nucleophiles or the weak nucleophiles. So you see, this is my ethyl alcohol. Ethyl alcohol, if you see, is a weak base. It's a weak base. Also, it is a weak nucleophile. Right? So, as I told, for nucleophile to be strong, it has to be a charged. There is no charge on this. So, it's a weak nucleophile. And it's a weak base. We know that it's a weak base. Now, if you see, this is the same thing, C2H5O minus. C2H5O minus. This guy has a negative charge. And this comes from nothing but C2H5ONa or C2H5OK. These are same actually, because this is nothing but Na plus and O minus. Correct. This is a negative charge, so it is a strong nucleophile. And as I told, that conjugate base is always a strong base. This is a strong base. So this is a strong base and strong nucleophile. So try to understand C2H5OH, weak base, weak nucleophile, but C2H5O minus is a strong base and strong nucleophile. Correct? So there's a difference between these two, right? C2H5OH and C2H5O minus. When you talk about C2H5O minus, you're talking about C2H5ONa or C2H5OK, right? Or C2H5ONa, anything that gives O minus, because it is a polar bond here. Now if you see NaOCH3, that is nothing but CH3O minus and Na plus. So this guy is this guy. It's a negative charge, so it's a strong nucleophile. And it's a strong base, right? Because it's a conjugate base, it's a strong base. But if you take CH3OH, this will be a weak base and weak nucleophile. Why weak nucleophile? Because it's neutral. And why weak base? Because we know that from the acid base chapter that CH3OH is a weak base. Right? This guy, if you see, is a weak base and weak nucleophile. If you talk about this guy also is a weak base and weak nucleophile. But if you talk about this guy, right, this is nothing but with a negative Na here, we can add here. This is the compound. This is a strong base. Why? Because the negative charge. But is this a good nucleophile? It has negative charge. It should be a good nucleophile, but it's bulky. It's a bulky nucleophile. So it is not that great nucleophile. You can say it's a weak nucleophile. Why? Because it's a bulky nucleophile. Correct. So if you see NaOH is nothing but Na plus OH minus. This is a very strong nucleophile with a negative charge, and NaOH is a very strong base also. So it is a strong base, strong nucleophile. So we have seen this is weak base, weak nucleophile, strong base, strong nucleophile. We have seen strong base, strong nucleophile. Here we have seen strong base but weak nucleophile, right? So we have different kind of combinations. So it is not mandatory that if it is a strong base, it has to be a strong nucleophile. or if it is a weak base, it has to be a weak nucleophile. It can be other way around also. Let's take some more example. You take NH2 minus, since it's a negative charge, right? This will be a strong nucleophile. And NH2 minus is a strong base, we know that. This one also, this was my amide, this was my methyl amide, right? So this is my strong base, you know that, and strong nucleophile is a negative charge. Correct? Same thing, dimethyl amide is again a strong base. Nucleophile, I'll say, is average nucleophile. Why? Because I feel that it has a steric hindrance. So it's average nucleophile. This one, again strong base. And nucleophile, I feel, is a weak nucleophile. Why? Why weak nucleophile? Because bulky. This is bulky. So you see, this is a strong base but weak nucleophile. Let's take this example. So this is acetylide. So this is also a strong base. And this is strong nucleophile also because of negative charge. Correct? This guy is also acetylide. This also is a strong base and strong nucleophile because of the negative charge. Let's take more example. Talk about I minus, B bar minus, Cl minus, F minus. So you get all these from, for example, NaCl will give you Cl minus, NaBr will give you Br minus, Ki will give you I minus. So this is the compounds which gives you I minus, Br minus, Cl minus, F minus. So you say these compound or these compound both are same. So in these compound, you see they all weak base. We know this. Okay. But they all have negative charge, so they are strong nucleophile. Correct? So these are examples which are weak base and strong nucleophile. You can take more. N3 minus, this is also weak base but negative charge, so it is a strong nucleophile. Cn minus also, if you see, it comes from KCN. So this is also weak base but a negative charge, so it is a strong nucleophile. Similarly, CS3CONa, that will give you a negative charge, CS3CO minus. This is also weak base but it has a negative charge, so it is a strong nucleophile. SH minus also, it's a weak base, know that, but negative charge, so it is a strong nucleophile. Similarly, SCH3 minus is a weak base but negative charge, so it is a strong nucleophile. NR3 with a lone pair here. You see, there is no negative charge, right? It's a weak base and it's also weak nucleophile. Similar, PR3 is also, I can say, average nucleophile because there is no charge and it's a weak base. Correct? We'll take water. Water, if you see, is a weak base, we know. And there is no charge on this, so it's a weak nucleophile. So it is a weak base and weak nucleophile. Phosphorescent, if you see, this is again example of a strong base, but this is a weak nucleophile. Similarly, this also, if you see, diisopropyl ethylamine, this is also a strong base but is a very weak nucleophile. Why? Because there is no charge and also it is a sterically hindered. We see that these kind of compound which are strong base and weak nucleophile, so they favors E2 reaction if you are using aprotic solvent. So aprotic solvent, you have only option of SN2 and E2. So in this case, these compound will favor E2 over SN2. We will discuss these in the next few slides. Thank you. Visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thanks once again.